are going to talk about transformers here. Now I want to make sure of one thing first. A transformer is not an energy conversion device. So this class is called electromechanical energy conversion. I'm going to turn that off. Okay. Electromechanical energy conversion. So it's not an energy conversion device. But it's a very useful part of any energy conversion system. It's an extremely important thing, and this is the one class where you really learn about transformers, I believe. So what we're going to start with is, I want to start with this core that we've been using before, and the one that we talked about in class last time, and where we derived the losses. So I'm winding around one leg of this core, and I'm going to be a little bit careful about defining my current directions to start with, to kind of make a point. Okay, so what's happening is I have a coil on the primary. It has a current through it, I1, time-dependent current, I1 of t, and there's also a voltage across the winding, and that voltage right now, I'm just going to say, is the voltage that is derived from Faraday's law, where we would say that E1 of t is equal to the derivative of what I'm going to call lambda 1 of t. Now on the other side of this transformer, we're going to put another winding, and in this case we're going to have it going like this. I'll talk about the current direction in a moment, but we will define the voltage this way on the other side. So the way when I'm applying these voltages, the arrow is kind of like the plus potential, if you're used to seeing plus minus. I like the arrows because plus and minus to me looks like a DC system, and an arrow is a more general way of looking at voltage potential. And now this transformer structure could be a very general electrical representation of the transformer. Looks like this, and I'm sure that many of you have seen this symbol in schematics, for example, and there's these little dots at the top of it, and you have your turns on the primary is on the left, the secondary has N2 turns, and the convention for these dots is to say that the current points into a dot. So I'm going to start with this convention. So there's a current flowing through coil 1 electrically. In the electrical schematic of this, it's pointing into the dot. And I will say that there's also a current flowing through coil 2, and I'm going to have it pointing into the dot as well. And showing the voltage potentials on each side of the transformer. Hey, I got to ask you all a question. Is my voice clear?
Yep.
Okay. I'm in the basement here. The heater just came on. I don't know how badly that affects things. But I don't want to freeze my wife out just because I'm teaching a class. Okay. So we have this. Now, if I were to say that the current is pointing into the dot in this electrical, that's the same thing as saying that the MMF from the secondary side is contributing to the flux that's flowing in the core. So let me explain what I mean by that. So let's apply the right-hand rule to the coil. I'll draw my cartoon hand here. Okay, so my thumb is going to point in the direction of the flux. It's an AC flux, so we're going to write it like this. And the AC current, I1, is flowing in the direction of my fingers. So I'm going to put the magnetic field intensity would be in the middle of this core. And remember again to remind everybody that I could have a magnetic core length. It's around that path, and there is an H in the core associated with that at that exact point in the middle of the core. There's a flux density of the core, remember, BC is mu H in the core, and the flux is flowing through the whole structure here, but we will just represent it, the flux line in the middle that's right along with the H. So what we've got is the flux being a time-dependent flux is flowing along this line. The arrow is pointing in the positive direction. When the current reverses direction, the flux will reverse direction also. But the reference direction is the direction of the arrow. And so what we're saying, because this arrow down here is pointing into the dot, if we can understand what I'm trying to say by looking at the magnetic circuit. The magnetic circuit of this structure has N1 times I, there's no dot on top of that 1 there, N1 I1 of T, applied MMF flowing through the reluctance of the core, and the way I have this defined right now, N2 I2 of T is in the opposite direction, so the two MMFs are adding up to the total flux. And so what that would mean, if I apply my right hand rule on the other side of this, I would have to point my thumb down. I'm not as good at drawing an upside down hand. Okay, and so this is the same direction as the flux there, but the current is flowing in my fingers in that direction. So I believe what I'm saying now is that the current is flowing into the coil. Okay, so that's I2 of T right there. And then we have this AC flux in our magnetic circuit. Okay, everybody with me so far? If there's no one... Yeah, go ahead.
Oh, no, you're good.
Okay, great. Okay, so now what I want to do is... just a second here, I'm going to check here. I've actually gone through this once. Double check my sequence here. Okay, so let's apply Faraday's law first to this structure. So Faraday's law says that E1 of T is equal to d lambda 1 of T dt. That the lambda is the flux linkage. It's linking the flux in the core to the coil 1. So that's the same thing as saying N1 turns times the... Now notice that I've got a core structure here with laminations. Remember we talked about those last time? And what does that mean? So that means that if I were to take a the core cross-sectional area, trying to do a decent job of explaining this. And it's slowing me down. So that's cutting through this core. Trying to show it. That's not quite the proportion here. If I'd have drawn by hand, it'd be a little easier, right? So you've got this core. There's a physical area of that core that I'm going to call area of the core. You could say that it consists of the length of the core, and then you could say this is a width here in this direction. So the B, the area of the core, the physical area, is length times width. But because we have laminations, the effective area is KSLW. So from last time we talked about that, this is the stacking factor. You remember that KS, it's your stacking factor, and it's less than 1. It's probably somewhere between 0.8 to 0.96 depending on the thickness of the laminations times the physical area of the core, and the Okay, so this is times the derivative of the flux density in the core and that's also the same as saying, so this is one way to write it if we want to consider that we've got a time varying flux density. Another way to write it is just n1 times derivative of the flux that is in the core. Okay, the if we look at the other side of the winding, so this is the primary side of the transformer and this is the secondary side. E2 is the derivative of lambda 2 dt. That's equal to n1 ks area of the core, or I'm sorry, n2 dvct dt, or we could write it as n2 derivative of the flux in the core. So what is the ratio of these two voltages? E1 of t over E2 of t is N1 derivative of the flux in the core over N2 derivative of the flux in the core these cancel. It's the ratio of the turns. So if we knew what the voltage was on the primary side, we could find the voltage on the secondary side. E2 would be equal, rearranging this whole expression right here, E2 would be equal to N2, let me make sure I got this right, so we're going to move that over here, we're going to move this over here, N2 over N1 E1 of t. Okay, so this is your first very important expression regarding transformers. The second one, let's talk about Ampere's law. So remember, we have this magnetic circuit that we drew up here. Oops. Okay, I just moved it. Okay, so there's the magnetic circuit, and we can really come up with what Ampere's law is telling us from this magnetic circuit. What Ampere's law is saying is that N1 I1 of t plus N2 I2 of t is equal to the reluctance of the core times the flux in the core. And so it's going to circle this because, or put a box around it because we're going to come back to it. If we have what I'm going to call an ideal transformer, which means that let's remove the nonlinearities. What would we have to do to make it? If we remove the nonlinearity, what anybody have an idea what we would do to this transformer to make it ideal? This is the class participation part. Got any ideas? No? Okay, we're going to operate in the linear region. Okay, so that means that the mu, the permeability in the core, would be approaching infinite. What happens to the reluctance of the core if the permeability is nearly infinite?
Isn't it almost zero?
That's right. It's almost zero, so the reluctance of the core approaches zero. If that's the case, then we can say n1 I1 of t plus n2 I2 of t is equal to zero. And now I'm going to rearrange this expression and come up with a relationship between the currents on both sides of the winding. So N1 I1 of t is negative N2 I2 of t. We can rearrange things here, and let's say what is the I2 of t in terms of the current on the primary side. It's going to be negative N1 over N2 times I1 of t. Or we could say, and I want to talk about this first, we could say that I1 of t is equal to the negative of N2 over N1 of I2 of t, the secondary current. Now we've got this negative sign here, and I don't really like the negative sign being there. And the reason why is because we're very quickly going to get to a point where we're going to use phasors, what we talked about in our module 1. And let's talk about, this is the periodic scalar form. These are sinusoidal, for example. They could be non-sinusoidal excitation. It could be, the current is close to a sine wave. If in the ideal transformer case we've removed the nonlinearity, definitely we're going to talk about sine waves, because once we start to introduce harmonics or distortion, then we introduce nonlinearities. So both these currents here are sinusoidal. So I could say I1 of t is equal to some I peak on the primary times, let's say, sine. Whether I use sine or cosine is arbitrary. I'll just use sine in this point because I'm trying to make sure I don't introduce another negative sign to confuse you even more when I take the derivative. That would be the same as saying the square root of 2 times the RMS value of the primary current. Now if I have this expression up here, it would say that I2 of t has to be equal to negative n1 over n2 square root of 2 I1 RMS sine omega e of t. That's also the same thing as saying n1 n2 square root of 2 I1 RMS sine of omega e t plus a pi offset. Now, I really want to look at all of my AC quantities. I want to say, okay, I'm going to start using phasors, and I want to analyze things with phasors. I know that my phasor representation of this whole thing here is, let's say, of this whole expression here, I1 phasor would be I1 RMS, and there could be let's be completely general here too. There's probably a power factor angle also. So I'm going to go back and add that in here. Okay, so, we're going to get to the point where we're going to be using these things here. I don't like the negative. Now, another way to think about this problem is, let's go back to this transformer here. If I'm inducing a flux into the core from the primary side, let's just say that this is the core due to the primary turns, the core flux. You all get what we're really getting to. We're getting to where a transformer is going to be, say, putting a load on the secondary side. So essentially I'm going to be getting to the point where I'm going to have, let's say, some load. Let's be more general here. We're going to have some load over here on the secondary side, and we're going to be applying some voltage here to the primary side. I'm going to be drawing current from this load. If I'm running at no load, I'm going to be operating at a certain flux density. If I draw more current, do I want the core flux density to go up or down when I'm loading this thing? Just give you guys a thought. Think about magnetic structures. I'm applying it to a practical situation. Remember, if we go to the BH curves and we have this BC, is, say, we're trying to design a transformer and we're trying to design it to operate around some maximum flux density, and I've got different design operational points. I've got a no load operational point, and then I've got a full load operational point when I start drawing current from the load. Do I want the load to increase the flux or reduce the flux? Question for time for class participation. Somebody say something. I mean, if it's the wrong answer, it's fine too.
Increase.
Increase the flux? Why would I want to do that?
Uh, to keep both coils are connected, so you need more flux in order to transform, electricity or voltage.
No, not necessarily. You have the flux already there being applied from the primary winding. You have a flux in the core, right? So what would happen if you increase the flux? What would happen to BC if you increase the flux?
BC will increase also. So that's mean we assume because in the linearity that's mean it's constant, but it's possible with a load effect will decrease.
Decrease what? Decrease what? The BC or what? Just asking you to kind of think about it. So basically, what I'm asking you is this. Here's your pH curve right here. You're operating right here at no load, okay? When you draw load, do you want to go up the curve or down the curve? That's the question. Any takers on that? Okay, yeah, I see what you... Okay, we got an answer here. You want the load to decrease that, don't you? You actually would like the load to drive you down the curve, not up the curve, because what happens when you go up the curve?
Professor, you're muted.
Oh crap. Okay, hold on. Hold. You guys hear me now? Sorry.
Now you're good.
Somewhere I accidentally muted myself. Okay. What I'm saying is, do you want to go up the curve or down the curve when you're drawing load?
Down.
Down. What would happen if you went up the curve? What's a bad thing that would happen?
Wouldn't you end up going into the straight part of the region?
Yeah, the saturated part, right? This is H proportional to current, the B proportional to the voltage, and you'd get what? More what if you go further up the curve? What bad thing would you get that we talked about last time?
Eddy currents?
Yeah, losses, right? You're going to have more core loss. So you definitely don't want to go up the curve. So what I'm saying is, if you think about the flux that's going to get produced on the other side from the other coil, you would really like that flux to oppose it, wouldn't you? The flux from the other coil.
Yes, you'd want it to oppose it.
Right, you'd want to go it down. So if that's the case, what do I have to do to my arrow of current?
Make it go the other way.
It's got to go the other way. Okay, so I actually want to go through this little exercise because I was going online and looking at the way people describe coming up with the turns ratios using Ampere's law, and they start the way I started here, and the meaning of these little dots. And people say, well, the dot is always the current's going into the dot. Now, I've always said this. On the primary side, the current goes into the dot, but on the secondary side, the current comes out of the dot. It's just a convention. I don't know, you can use these dots for understanding how you're winding coils around a core and representing it in the electrical circuit. So let's just come up with this convention right now for the transformer. The arrow goes into the dot on the primary, the arrow goes out of the dot on the secondary. Okay? Does that make sense?
Yep.
So if I do that, what have I just done? Well, if I go down to what I came up with the Ampere's law, I just got rid of this negative sign. And now I've got something that's a lot easier, better to work with. So essentially, I can now say that I1 of t is equal to n2n1 I2 of t. So from this, we can say the ratio of I1 of t to I2 of t is equal to n2 over n1. Remember, we went up here and we'll see what we did this with the voltages. It was n1 over n2. So it's the opposite, n2 over n1. If my voltage is going to go, if the transformer, let's say, is going to boost up my voltage, it's on the secondary side, the transformer is going to boost, it's going to buck down my current on the secondary side. I can also say that the secondary current I2 of t is equal to n1 over n2 I2 of t. And typically when you look at a transformer, so we're getting more to a much more practical type of transformer shape. I've got the current going in the primary. I've got my current coming out of the secondary. I've got the voltage applied, and I have the voltage that comes out on the secondary. You could apply voltage on either side, but we're just kind of defining it right now that the voltage is being applied to the primary and measured on the secondary, and I actually am going to put a load on that. So I have my voltage right across the coil, E1 of t, E2 of t here, and there's another thing I can do with my turns ratio. So I have, typically you put this little colon here and you put your turns on each side, but if I were to divide both sides of the turns ratio by n2, I'd have a n1 over n2 to 1 ratio. This is the common way that transformers are represented. So what is n1 over n2? n1 over n2 is defined as turns ratio. And a standard symbol that's used for that is A. A equals n1 over n2. So I could replace this with A on the So we could redraw this thing like this. A to 1. If that's the case, then let's take a look at these relationships that I have. First of all, we had up above, we talked about the ratio of the voltages, E1 of t over E2 of t is equal to N1 over N2, or A. So I could say E2 of t is equal to E1 of t divided by A, divided by the turns ratio. Now we had the current right here, same expression. I can say I2 of t is equal to turns ratio times the current on the primary side. Does that make sense? Any questions about that?
Yeah, I got a quick question.
Yeah.
For the dot convention, so that we won't have a negative, is that just for this class, or is that standard?
Standard, pretty much standard practice.
Okay, gotcha.
Yep. I mean, it's every time I look like a transformer, that's what I never think about the current going in. If you go on some online classes, people point the current in, and to me it doesn't make sense, because I'm saying I'll tell you why. Here's one point. That is a good question. I'm going to show you something here. And we're going to talk more about this. So here's where we're heading. I might put a voltage on the primary side of the transformer, and I might have a load on the secondary side of the transformer. So in this case, my arrow is pointing into the dot on the primary, and it's coming out to the load on the secondary. Completely makes sense, right? If I went the other direction and I wanted to put my spread this out a little bit here. I'm going to put the load on this primary side and apply the source. Apply from the secondary side. I would want current to flow in the other direction. So in this case, I would want my current to go this way. Right? Does that make sense?
Yeah.
So we're thinking about it in terms of the source and the load. Current flows into the load, flows out of the source, as far as our convention of the arrow, the pointing of the arrow. It's an AC current, so the current and the voltage go positive and negative, but we define the positive convention as going from source to load. Okay, so now what if, let's go and let's now consider the non-ideal transformer, or I'll say realistic transformer. So to do that, let's go back to what we had right here. It didn't go in the right place here. Okay, so here's that magnetic circuit, but remember that we changed the direction of the MMF, the current. So what we did was I changed this, so it's like this. So now the flux coming out due to the secondary MMF would be opposing the flux from the primary MMF. And I can rewrite my Ampere's law expressions as N1 I1t minus N2 I2 of t is equal to the core reluctance times the flux in the core. So I just, before I had a positive sign right here, and now I've got a negative sign. Now what I really have is there is the flux in the core is equal to, rearranging everything, that's the flux in the core. And now what I want to do is I want to take the same transformer structure and let's talk about the flux linkages on each side of the transformer. Think of it in terms of applying a flux linkage. So lambda 1 is equal to this. We've got this flux right here that we're going to work with, okay? Lambda 1 is equal to the turns of the primary times that flux. N1 times N1 times I1 of t minus N2 I2 of t divided by the reluctance of the core. And let's pull out the N1. And let's pull out the reluctance of the core. Remember that when we talked about inductance, it really, the general expression for an inductance is the turns squared, or the product of the turns if it's a mutual inductance, over the reluctance. And so what I have inside of here ends up being a current I1 of t minus N2 over N1 I2 of t. And I can call the current, this current right here, is what generally is referred to as the excitation current. And we can rewrite it this way: N1 squared over RC times I phi of t. So that's the flux linkage looking into the primary side of the winding. Now we know that L is lambda divided by I in general, whatever current was applied. So we can come up with something that we're going to call a magnetizing inductance. Really, we're looking at the transformer as an inductor now from the primary side. Lm, and I'll just put a little subscript 1 to say this is the magnetizing inductance looking in from the primary side, is equal to lambda 1 divided by the excitation current, which is simply N1 squared over the reluctance of the core. So we have Lm1 equals N1 squared over core reluctance. Now let's look from the secondary side. Lambda 2, starting up at the beginning here, would be the secondary turns times the flux in the core. So that's N2 times flux in the core is the same as before, N1 I1 of t minus N2 I2 of t over the core reluctance. In this case, what I'm going to do is I'm going to pull out the N2 and pull out the RC. So I'll have N2 squared over RC and that gives me I N1 over N2 I1 of t minus I2 of t. Now what I'm going to call this is I prime of the excitation current. Now what do I mean by this? I prime of t is the primary side excitation current I phi of t referred to the secondary side. So what this means is that I can actually, you can refer quantities to either side of the transformer. And this is a very powerful thing that will help us solve problems with transformers. We're going to come back to this, but basically right now just I'm highlighting this and we're going to come back. But we're going to be able to derive a magnetizing inductance seen from the secondary side. and that is going to end up being an Lm sub 2, and it ends up becoming N2 squared over the core reluctance. Basically go through the same exercise that I went through before, essentially saying that Lm2 is equal to the lambda 2, which I found right here, this is an inductance, right? That's Lm2 right there, times that. And then what I've done is I've essentially divided out the secondary referred current to get that. Now let's take a look at this transformer as if we're looking at impedances from either side. In order to do that, we're going to make a segue to phasors. So first of all, let's take a look at the coil. The voltage on the primary is the derivative of lambda 1. The voltage on the secondary is the derivative of lambda 2. And this is I1 of t, and this is I2 of t here. And so I'm going to go back and look at what is lambda 1. Lambda 1 is Lm1 times this excitation current, and lambda 2 is Lm2 times the excitation current prime looking from the secondary side. Let's just work on the left-hand one here first. And let's define, see, did we already do that? Where did I have the currents? No, we didn't do it, not for excitation current. So let's define I excitation as square root of 2 times I, let's do this the opposite way, I excitation RMS. This is going to be a quantity we're going to talk about a lot. That's the peak current of the excitation current. And there's a power factor angle which I'm going to call phi c. Later, this will be referred to as the no load excitation current. on the primary side. Now the I, recall that we defined I. What are we really doing? Okay, let's draw a schematic to help ourselves out. What have we done to this circuit here? We've got just about 3 minutes left. We're almost to where I wanted to be. We've actually added an inductor. Right now I'm going to look at it as this way, to the primary side. I can only put that inductor on one side of the transformer, the primary or the secondary, because we're really just considering one inductor. I've got a current, I1 of t, coming in here. This current down here is I excitation current. And we know that we've got a current on the secondary that we call I2 of t right here. And we have this turns ratio A to 1 on either side of the transformer. Remember that we said that I2 of t is equal to A times I1 of t. I can also say that I1 of t is equal to I2 of t divided by the turns ratio. And now the what I just did here is I could say that this is not really I1 of t because I've added this branch here. Before I have these currents, I could move them around however I want without having to worry about what I'm calling them. But what I'm really going to do is, this is really not the appropriate way of referring to this quantity. I'm going to call this I2 of t prime. I'm going to use the prime number, the prime, whenever I move something from one side of the transformer to the other. So this is the I2 of prime, where we are referring secondary current to the primary. So what that is that is this. This is I2 prime right there. I've moved it on the other side of the transformer, and I really have here a current node. And so I excitation current is equal to I1 of t minus I2 prime of t. And we defined I2 prime of t as I1 of t minus the actual I2 of t divided by A. That's the same as saying I1 of t minus N2 over N1 I2 of t. So the last point I'm going to make here is, what is this? let's go back all the way to the beginning right here. Does this look familiar? We should have that been down here. And we do, right? So the excitation current is I1 of t minus N2 over N1 times I2 of t. And anyway, we're going to have to stop right there, and we're going to pick it up here. But where we're going with this whole thing next time, and then we'll have everything we need. We put losses into the picture, and you've got everything you need to solve all the homework problems. We're going to look at impedances from the looking in from the primary side, and impedance looking in from the secondary side, and we're going to be able to derive turns ratio relationships between primary and secondary quantities of voltage we've already done, current we've already done, and then we'll have impedance, and then we've got everything we need to solve any transformer problem. Any questions? I know we're 2 minutes over. Is it clear, or did I lose people, or am I muted?
Pretty clear.
Pretty clear? Good. Okay. All right. Well, if there's no questions, we can end here, and then I'll just stay online if anybody wants to ask me any specific things in the next, say, 10 minutes. And I will post these OneNotes directly onto the Teams meeting now. So I figured out a much better way to handle my lecture notes. So you'll have that as well, and then I'll clean these up, put them into a PowerPoint, and that will be the usual lecture notes that go up on Canvas.